Thank you very much for inviting me. I was a bit surprised to see that I have to give not have to, but I was invited to give a talk here. So I didn't know what to do because nowadays I'm not working on this type of problem, but then I thought I'd talk about some work from about 2 years ago. It's not that old, with Gautam and his students at that time, Anurag Kaushal and Advait Gaikwad. So Anurag might be in the audience because he's a postdoc here. So anyway, so I thought I'd tell you something about the problem of black hole evaporation, which is a very difficult problem in higher dimensions, but let me see. So just a brief background, because we are from different subjects. Black holes are solutions of Einstein's equations of general relativity, and they exist in nature. And this we can see them now by the Event Horizon Telescope. And now back to theory. In the presence of quantized matter, black holes are thermodynamic objects, and they are characterized by their mass, entropy, and temperature. And here is the famous formula of Bekenstein and Hawking. And please note that there is an H bar here. This is a quantum mechanical formula. It doesn't exist in classical theory. Okay, so this is the famous calculation of Hawking about the temperature of the black hole. Again, it is quantum mechanical, and for the black holes which were considered by Hawking, they were black holes of the Schwarzschild type in a space-time which is unbounded, like possibly our universe actually. And so the problem is that such black holes have negative specific heat, and in fact it is not possible to describe them in the formalism of standard equilibrium statistical mechanics, because the partition function is always divergent. It's because this factor entropy grows as m square and quickly overpowers the Boltzmann factor. And so non-equilibrium dynamics of such black holes is a very difficult, complicated problem. And so we do not know how to handle it. But as physicists, we always try to invent a model in which we can solve the problem. So, this talk is about black holes in what are called anti-de Sitter spacetimes, and the simplest example of the anti-de Sitter spacetime is the upper half Poincare plane. I mean, since this is Indo-French, I thought, this is a great contribution of Poincare. So that's the simplest anti-de Sitter space, and in such spacetimes, the basic physics problem here is that space-time actually, gravity becomes very strong asymptotically, so it's like putting stuff in a box, a gravitational box. And then we have well-defined statistical physics, finite partition functions, and we can compute things, and these black holes are in equilibrium, okay? So when the black hole emits, it also absorbs because there's a reflection from the walls, and you have a well-defined system to work with. All right, this is a cartoon of the famous ADS-CFT correspondence. So what I'm saying is that there is a certain space-time called anti-de Sitter space, which has a boundary, and there's a black hole inside. And one of the big realizations of the past 25 years or more perhaps is the fact that we can describe this object as an object in standard statistical mechanics if we look at it from outside, and more so, we can find a hologram of it on the boundary of this theory. And this is the famous ADS-CFT correspondence of Juan Maldacena, discovered in 1996 or 97 or something like that. Now, as I said, this black hole is in equilibrium. So if I want to study the evaporation problem, I need to couple it to a bath, to an external system into which the radiation can escape. Okay. So this is the problem that I will want to discuss with you, but I will now go down in dimension so that I can do calculations, and very much like some of the calculations we saw in some of the earlier talks in this session. Okay, so we will study the case of d equal to 1, that is and ADS2, antidisturb space in 2 dimensions, and we can imagine that this type of black hole descends from a higher dimension, and all those details are not important for this talk. And we couple this system to a 1 + 1 dimensional quantum field theory of just massless scalar fields and study the evaporation process using, and that's the point actually, using the SYK model. So SYK model was invented for studying condensed matter systems of a certain type, but it has been found very useful in the last decade or so to use it to discuss black hole physics. So this is again a lot of cartoons and then lots of calculations afterwards, don't worry. So here is 2-dimensional gravity. There's a black hole inside. This is the boundary of 2-dimensional gravity, and it's coupled to a bath. So this is the physics problem we want to really study, which I have it's a more technical picture over here, but it's the same as this, that how does the black hole interact with the bath and evaporate? And this problem is equivalent by this duality ADS-CFT correspondence to studying how the SYK model interacting with the bath, the states, the black hole state, which I will mention about, evaporates, okay? All right, so one slide on the SYK model. I think most of you must be knowing it. It's a model of n real fermions. The dimension of the Hilbert space is very large if n is very large, and it has a Hamiltonian which has, all-to-all interaction of 4 fermions. You can take any number of fermions, but I'll stick to 4. 2 is no good because you get a spin glass phase. That's not interesting for us. And the random interaction is just Gaussian, as indicated over here, and normalized in the proper way. So some results of the large N analysis of this model at low energies. The most important point is that there exists an infrared fixed point, and there's an emergent reparameterization symmetry, and the low energy degrees of freedom of this model, believe me, are just 1-dimensional maps. So if time is real and extends from -infinity to +infinity, the functions f of t are valued in diff R1 but modded out by SL2R. Please don't ask me to explain the modding out by SL2R, that's technical. But if you're working with Euclidean time, so that time is on a circle, then the group, the functions are sort of valued in diff S1 mod SL2R. And whenever you have low energy degrees of freedom, they are sort of governed by some effective action, and that effective action is this famous Schwartzian, okay? And there's an n over here, it's a large n, there's a factor of j over here for dimensional reasons. There are 2 very important consequences of this model besides the infrared fixed point, which dictates this, is that the density of states of this model essentially can be calculated, and it goes like this. So for small energies, it goes as square root of E, like the Wigner law, and for large E compared to J, it essentially is an exponential. The other important property of this model, which makes it relevant to understand black hole physics, is the fact that the OTOC, or the out-of-time correlator, grows exponentially with a Lyapunov exponent that is maximal, that is 2 pi upon beta, beta being the inverse temperature, okay? So because of these properties, this model is a good model, mechanical model to describe an object in gravity, which I do not understand too well, actually, in terms of gravitational degrees of freedom. But this duality can be used for us to learn something. Okay, so One slide on JT gravity. I won't spend much time except to say that it so turns out that the degrees of freedom of JT gravity are exactly the same as the SYK model, and then you can actually talk about these one-dimensional maps, which are the low energy degrees of freedom, giving rise to a certain formula for the metric of the physics inside the bulk gravity. So this model has you can vary f and write down a classical solution, and it so turns out that these classical solutions, this very simple classical solution describes essentially a black hole spacetime. Okay, it's a very beautiful thing that the boundary degrees of freedom, the equations of motion of the Schwarzschild give rise to a black hole metric. Okay, so this can be done in Lorentzian and also in Euclidean spacetimes. Okay, so this is just a cartoon of a Penrose diagram of this black hole which I'm talking about, and as I said, the explicit formula is here in terms of what are called Poincare coordinates. These are technical things, but the important point I want to make is that we want to study the dynamics of this particle described by f of t on the boundary of this space-time. And this dynamics is controlled by the SYK model. Okay, so here is once again this formula rewritten in this very suggestive way, so that the particle starts from here and sort of ends over here, ends its life over here. And the important point, and this is the crucial point I want to make, is that here there is a diagnostic of the presence of a horizon or not, which characterizes the black hole geometry. And it's the following, that if this f function f of t, which is a map from t to f of t, has a vanishing Jacobian like this over here, then the space-time must have a horizon. I cannot explain this in great detail because I have very little time, but this is the diagnostic of the appearance or disappearance of a geometry with or without a horizon. Okay, so let me continue. As I said, so now what we'll study basically is the dynamics of the curves f of t when the system is coupled to a bath into which the black hole can radiate, and this is where I'll make contact with this conference now. So the first thing about the SYK model which I have to tell you is how do I model a black hole state? Now this is amazing that in this beautiful model you can actually do that. So let's first look at this type of operators which are made up of these real fermions, odd one and even one. Okay, the square is 1, so the eigenvalues are plus or minus 1. So these operators and their eigenvalues essentially form a basis of states that span the entire Hilbert space of the SYK model. Okay, and the black hole state basically is proposed, it's a proposal, to be essentially a low energy projection of this state. This is a very high energy state in a sense which I don't want to get into, but if you have a low energy projection where L is very large and we are at very low temperatures, then this is the proposed black hole state. This is a candidate. And this was proposed by Kulkuru and Malasena some time ago. Incidentally, this paper never got published. I don't know why. Anyway, this is a very important paper. And the important point here is the fact that if I take, for example, any set of operators of the SYK model, which are, let's say, ON invariant operators, then the correlation function in this state, so-called black hole state, can be shown exactly, this is a simple exercise, to be exactly thermal. So in this sense that this state essentially behaves like a black hole state. And however, it cannot thermalize all operators. For example, there are operators like the spin that we talked about, which are odd under this simple symmetry. And for those states, so those operators, the states and correlation functions are not thermal. And this, I think, is the key insight of Kurkuluri and Maldacena, that operators that don't thermalize can give you some insight into the microstructure of the black hole. Okay, so these operators are the following. As I said, this S is odd under the flip symmetry, and so we consider these operators. And you can calculate the expectation value of this operator in the black hole state, proposed black hole state, and it turns out to be calculable. And then you can compute the low energy formula for the thermal Green's function at this complex, in the complex time plane, and it turns out to be this. So, I mean, this is just calculations. So, this object basically goes to f dot raised to half. The expectation value of this spin operator is just f dot raised to half. Then you look at the next one, and the expectation value over here essentially turns out to be minus of f dot upon 4 pi. So these are all precise calculations you can do in the large n limit and calculable large n corrections. So important point is that everything I do, I can compute corrections actually, okay? And henceforth, we will call this Jacobian f dot as exponential of phi, where phi is just some scalar field. And it's because we have to sort of make sure that this doesn't become negative, okay? All right, so now let me pose the problem. The problem is that I have this SYK model coupled to a bath. I have given you the set of operators in the SYK model which I will couple the bath to and study the non-equilibrium dynamics, okay? And it so turns out, after a lot of trial and error, we found that this combination which I mentioned before, this is the operator which is linear in the spin, this is the operator which is quadratic in the spin, with two couplings, control parameters of this problem, which later on I will need to even have some time dependence in these control parameters, is the solution. We found after a lot of trial and error that this is the operator to couple to the bath from the SYK model. So you have this bath conformal field theory of NF scalar fields, with the number of scalar fields is much less than n, which is the number of species of the SYK model, and this is the coupling, just proposed coupling. Here is the full story, that the interaction therefore is given by the bath fields or the conformal field theory coupled to the SYK model with this precise couplings, and this is the SYK model, and then there is the simple Hamilton or action of the massless scalar fields. Okay, so here is our action, and there's a corresponding Hamiltonian, of course. So I have sort of laid out for you the evaporation problem I am sort of going to try to solve. And so this is now very standard stuff which I'm going to talk about, Schwinger-Keldysh method, which is the right formalism to discuss this problem, because we want to talk about the evolution of the density matrix. So here is the point. We start with an initial density matrix of the SYK model and the conformal field theory. It's pure, rho square is rho. And I want to evolve this in terms of this total Hamiltonian, which I talked about before, and compute averages of operators. And we always work in this approximation, low energy approximation, and at large n, where the Schwarzschian description in terms of these low energy degrees of freedom is valid. Okay, so very good. So the point is that, we couldn't find, it took some time to realize what is the coupling to use to have complete evaporation. For example, if this G prime, the S square coupling is not there, then the black hole evaporates to a black hole of a smaller mass. Okay, all right. So So this is setup of the density matrix. I'm not going to tell you all the details. This is given in terms of the black hole state, and the conformal field theory density matrix is given in terms of a squeeze state of this free scalar field theory, and the state looks something like this. It has a parameter which sort of acts as the temperature of the bath, capital L, which is very large. Okay, so there are a lot of technical things over here. We have to be very careful about cutoffs and stuff like that. Everything can be calculated and correctly done. So, all right. So now this is the formalism, which I think all of you must be knowing, perhaps a little bit much more than me. This is the Schwinger-Keldysh method of evolving the density matrix. So there are two contours because you have to go forward and then come back, right? And we want to compute something like this, basically. So you want to average over the bath degrees of freedom completely, and therefore you arrive at this influence functional. This is the Feynman-Vernon influence functional in this problem, and it is sort of given in terms of 4 kernels as usual, because you have 2 contours over here, and so there is an effective action that you can write down. This is the effective action that you have to work with this kernel, with this phase, sorry. Yeah. So now you just grind it. I mean, you just do it. So we introduce this Keldysh's trick, which is very important. So define the linear combination of the fields on the 2 contours, plus and minus, and we call it phi q, and this is phi c, and then you can write down the theory in terms of these objects and integrate out the phi q, okay, in perturbation theory in 1 upon n. And if you do all this, there's a whole process which is textbook stuff actually. You essentially arrive at this quadratic action, and then you introduce a noise term, basically by rewriting the quadratic action in terms of a path integral over a Gaussian noise. It's all standard stuff, and you arrive at the mathematical problem that you have to solve. This is a stochastic differential equation which has a Gaussian noise which is so-called colored, and the kernel actually is very long-ranged and complicated. So this is the mathematical problem that you have to solve to understand the evaporation problem of the black hole in this simple situation. Okay, so I will now basically tell you very quickly how this is done, all numerically, and we'll arrive at some conclusions actually. Okay, so all right, I also learned in this subject that these type of equations are used in financial mathematics, so that's very nice. I thought maybe they can pay us some money actually. All right, so okay, so well, this is a math slide, so we can rewrite this equation in terms of local equation of 3rd order in time. There are no runaway solutions, you can check that. So I have a certain question for the audience, that if I rewrite this equation in terms of 3 variables now, x, v, and acceleration, I get this type of equations with the noise term. So you essentially have 1st order Langemann type equations with this noise terms. So the question is, can one find a Kolmogorov-Fokker-Planck type of equation for the probability as a function of x, p, and a? I couldn't do it actually. This is you can't write down for even though
you can extend to higher on these things, but then you have to have a delta function for the market processing.
I see. Okay. So this is the no-go theorem. Thank you. Okay. All right. Okay. So now let's try to solve this problem. So we write phi c as phi plus a fluctuation which is down by 1 upon root n, and this is the classical equation and this is the fluctuation equation. And now basically, one just solves this problem, and this is the answer. So it's all done numerically. It's a lot of heavy lifting, which was done by the students and Gautam, and I'm not very good in all this numerics, but these guys are good. So the point is that there is a region given by this dotted line outside of which the solutions are divergent actually. There are no well-defined solutions. In this red region, this is the G prime plane. These are the control parameters of our problem. You have a solution in the red region which asymptotically goes to minus AT, which means that F dot goes to 0. Means all of these guys over here will go and become small black holes. It won't evaporate. It is the green region over here. There is a non-zero region in which phi of t is always bounded as a function of time, which means that F dot, the Jacobian, is never 0 and there is no black hole asymptotically. So the horizon goes away. So this is the sort of signature, classical signature of the black hole evaporation. And I just wanted to tell you that, a lot of numerics went into this type of cartoon picture, which I made sure of this actually, asking people to look at more and more and more points till we understood that our cartoon diagram actually is substantiated by the math. Okay, so this is an example of a solution that blows up, and okay. Now this is the example of more precisely the solutions in the red region of the G prime plane. As I said, they essentially go to smaller black holes, and now the solution in the green region. This is the region in which we expect everything to evaporate, and this is how it looks like. There's a lot of oscillations around a certain line in the phi t plane, and the oscillations are all around value of f prime equal to 0. I mean, these are some details you can see in the paper. That's not important. Now we consider solving we can do this analytically, this one, in terms of Airy functions. And so you do it and you arrive at something very important. What you arrive at is essentially a simple differential equation for these oscillations, but with a frequency which is growing in time. So that's bad news, because we said that our approximation was a low energy approximation in which the frequency was small compared to the parameter j. But here, what to do? So since we are modeling evaporation and the control parameters are in our hands, what we did was basically quenched the control parameters beyond a certain maximum time. Okay, so we just decoupled the bath in this particular specific way. Okay, this goes as 1 upon square root of t, this graph. And then redo the whole analysis actually. Then you find that the frequency square stabilizes nicely, and you can now solve the problem analytically for f dot, which is given by these functions. It's very simple in terms of these asymptotic parameters. I don't want to, sorry. We do the numerical, again, the numerical analysis, and we find a nice numerical solution for the classical equations in which the quench protocol is such that the solution stabilizes and it is always bounded, indicating that the final state of the system is no black hole. It's just completely evaporated into the bath, okay? Because of this diagnostic which is there in this simple model. Okay, so this is the sort of geometry picture of what happens. So, I mean, the evaporation basically is this green region, complete evaporation. This is the red region, partial evaporation. Okay? And the last part of this talk is basically, now what about fluctuations? So one of the things we understand is that the process of black hole evaporation towards the end is very stochastic. There's a lot of fluctuation actually. And Lognayagam explained this to me once in a very simple way, that take a drop of water and look at the dynamics of evaporation. This is not simple, but you will expect that as the drop is just disappearing, the fluctuation is very large, which is sort of obvious. And this is the reason why you expect a lot of fluctuations when you solve this type of problem. So the fluctuation equation essentially is a linear equation in C, which is the fluctuation. So we can just solve this. We can solve it numerically, and this is the solution. Just tell you the solution of this equation. Turns out to be just this, and you can identify over here, just a standard diffusion constant, which goes as the temperature of the bath. 1 upon L, as I said before, is the temperature of the bath. And this is in the red region for partial evaporation. And for complete evaporation, what you find is essentially this oscillations, which is characteristic of Brownian motion in a bounded potential. If you solve that problem in a textbook level problem, you'll find this type of a solution. Okay, but there's one thing important actually, that if you plot, for example, the correlation of the fluctuations with the temperature, you find that the temperature dependence at fixed time is not linear actually. So this is the characteristic of the end point of evaporation. Okay, and well, this is the summary. I'm at the end of my talk. So we have demonstrated the dynamics of black hole evaporation in the SYK model, which is holographic to JT gravity, and the SYK model is coupled to a bath, a specific type. It's a conformal field theory, and the calculation is done in the low energy approximation using the Schwarzschild mode. It describes the geometry in the dual JT gravity. Thank you very much.
Long live India and France friendship.